Hi, I'm going to talk you through the exam questions on fission and fusion for 27.3. Okay, so question number 1. Diagram shows how the binding energy per nucleon varies with nucleon number. And they've given you oxygen 816 on there. Here's the binding energy per nucleon. You can see the maximum there just below 9, that'll be iron. And then you've got the nucleon number here. And it says fission and fusion are two nuclear reactions, processes in which energy can be released. Explain why the nuclei that undergo fission are restricted to a different part of the graph than undergo fusion. So you need to say that fission are to the right of the peak, and by doing fission the nucleus splits into two smaller parts and they gain more binding energy per nucleon and move towards the peak. You then need to say that fusion are to the left of the peak. When they increase in size, they increase their binding energy per nucleon and they move towards the peak this way. Okay. Part 2. Explain with reference to a diagram why the energy released per nucleon from fusion is greater than that from fission. So you need to say that when the binding energy per nucleon is increased, there is a release of energy. And that fusion, when things do fusion, the change in energy is greater than when things do fission. Okay. So that means that when things undergo fusion, there's a bigger increase in the binding energy per nucleon than when they do fission. Part B1 says calculate the mass difference in a kilogram of the 1610 O nucleus, and it tells you the mass of that nucleus. So we've got that, so we need to be able to use delta M equals ZMP plus A minus Z Mn minus M nook. So the change in mass, this will give us it in U. So we've got 8 times the mass of a proton plus 8, because 16 minus 8 is 8, times the mass of the neutron minus 15.991. This gives me a change in mass of U of 0.1366 U. 1 U is equal to 1.661 times 10 to the minus 27. So my change in mass in kilograms is going to be 0.1366 U times 1.661 times 10 to the minus 27, which gives me 2.3 times 10 to minus 28 kilograms, to two significant figures. Part 2, using your answer to B part 1, calculate the binding energy in mega electron volts of the oxygen nucleus. So I'm just going to use the fact that the change in mass was 0.1366 U. I know that 1 U gives me 931.3 mega electron volts. So I'm going to find the binding energy as 0.1366 times 931.3, which gives me 127.21558, so 130 mega electron volts to 2 sig fig. And it says explain how the binding energy of oxygen can be calculated with information from the diagram. So what you would do if you had this diagram, which I've now put somewhere, here it is you would, if you read off the graph here, here's the oxygen, the binding energy per nucleon is 8 mega electron volts from the graph. And you have 16 nucleons. So 8 times 16 gives you 128, which is 130 mega electron volts to 2 sig fig. So you need to say you'd read the binding energy per nucleon from the graph, and then you'd multiply it by the number of nucleons. Okay. 2a, state what's meant by the binding energy of the nucleus. So again, you need the definition of binding energy, which is the work done to remove all the nucleons from a nucleus. And here we've got a 235 uranium nucleus absorbing a slow-moving neutron, undergoing fission to become 2 parts. Complete the following equations. Basically, you need to figure out how many neutrons you need. So the top number on this side is 1 plus 235. So that equals 236. And on this side you've got 112 plus 122. Okay, which equals 2, 3, 4. So I'm missing 2. Just check the bottom number. You've got 0 plus 92 equals 43 plus 49, which equals 92. So that's right. So I know I need 2 of these neutrons to complete the equation. Part 2 asks you to calculate the energy released when the single uranium nucleus undergoes fission in this way. They've handily given you some numbers here, so this is great, but they've given you the binding energy per nucleon. So the mass of the products will be greater than the mass of the uranium. Okay, so we're going to do these two added together and then take away this, and that will give us the amount of energy. So these are the binding energy per nucleon. So we're going to do the first one, the first product, which was the TC. So we've got 112 nucleons, and each nucleon gives us 8.36. We're going to add on the 122 times 8.51. That's these two added together. And then we're going to take away the original mass, the energy of the nuclei. So that is 235 times 7.59. Okay. And that will give me the change in energy. It works out to be 190.89. So that's 190 mega electron volts to 2 sig fig. It says calculate the loss of mass when the 235 uranium undergoes fission in this way. So I know I've got 190 mega electron volts, and I know that 1 U would give me 931.3 mega electron volts. So I know it's changed by less than a U. So the change in mass is going to be like what fraction this is of this. So I'm going to do 190 over 931.3. In fact, I'm not going to do that. I'm going to do 190.89 over 931.3. So I'm going to use my actual answer here. So 190.89 over 931.3. That is 0.204971545 U. And then 1 U is 1.661 times 10 to the minus 27 kilograms. So I'm going to do, the change in mass will be 0.204971542 times this value. And that will give me my answer in kilograms, which works out to be 3.4 times 10 to minus 28 kilograms to 2 sig fig. Then on the figure, sketch the graph of neutron number against proton number for stable nuclei. So the first point, N equals Z, for values of Z smaller than or equal to 20. So that's that. And then what you need to do is also mark on the point Z equals 80, N equals 120. Here, and then the first one you definitely need to draw with a straight line, and then it curves up. Okay, we've done that question before. And then C part 2 says, with reference to the figure, explain why fission fragments are unstable and explain what type of radiation they'd like to emit. So the fission fragments have they're basically neutron rich, so they're up here. So that means that they're unstable because they're to the left of the graph. So to become stable, they either produce beta minus, so the neutrons are turning into protons, so they're reducing neutron number and turning into protons, or they can just emit neutrons as well, which we haven't really talked about before, but they can give out just neutrons, neutron decay. Question 3. The figure below shows the variation in binding energy per nucleon with nucleon number. So you've seen this graph before. They've given you 3 values on here. And it says a uranium-235 nucleus, so this one, undergoes fissions of 2 approximately equally sized products. Use the data from the graph to show the energy released as a result of the fission of this is 4 times 10 to the minus 11. So let's do that. It's worth 4 marks, so it's quite a big question, but it's really, really easy. So first thing to do, let's find out the binding energy per nucleon of uranium. So to do that, get your ruler, draw a line across here, and you get 7.6 mega electron volts. You also then need to find the products. So 235 divided by 2, because it says it divides into 2 equal parts, is about 118 to 3 significant figures. So on the graph, draw a line across where A equals 118. And that is equal to 8.2467. So the difference in binding energy per nucleon is equal to 1.1 mega electron volts. We want the difference in energy, so we're going to do find the EB, so we're going to do 1.1 times the number of nucleons that you had. So 1.1 times 235, so that gives me 1.1235 mega electron volts. And then 1 mega electron volt equals 1.6 times 10 to the minus 13 joules. So if I multiply these two together, that gives me 1.1235 times 1.6 times 10 to the minus 13 gives me I've made a mistake. Oh, it's here. Why have I done this? This is wrong. 1.1 times 235. 258.5 mega electron volts. Okay, so now I'm going to multiply those two numbers together. I was thinking that's not what I wanted. Okay, yeah, so I get 4.136 times 10 to the minus 11 joules, which is what you wanted here. Sorry about that mistake. I bet you all picked up on it when you were watching me working. Right, so that's worth 4 marks. Third of a grade. So using the data below, show that the energy available from the fusion of 2 hydrogen nuclei to make a helium-4 nuclei is this. Okay, so you're going to do this. This is your fusion reaction. 2,1 plus 2,1 hydrogen goes to make a 4,2 helium. Okay, this is lighter than these two, so there's a change in mass. So you're going to do 2 times the mass of these two, 2.0135, and you're going to take away the mass of this one, 4.0026. That gives you a change in mass in U of 0.0244. 1 U equals 931.3 mega electron volts, so my energy is going to be 0.0244 times 931.3, which gives me 22.72372 mega electron volts. I need to convert that into joules, so my change in energy is my energy in mega electron volts times 1.6 times 10 to the minus 13, which is the energy in joules of 1 mega electron volt, and you get 3.6 times 10 to the minus 12. With rounding and stuff, you might end up closer to this, but that's good enough. And it says compare the energy available from one complete fission of 1 kilogram of uranium with the energy available from fusion of 1 kilogram of hydrogen. So let's do the uranium first. We figured out that 1 uranium would give you 4.136 times 10 to the minus 11 joules of energy. So we need to figure out how many uraniums we're going to have in a kilogram. So the number of uraniums, the number of moles is going to be 1,000 divided by 235, which gives me an answer of about 4, ish, because I'm only comparing, so that gives me an answer of about 4. So the number of molecules I've got is 4 times Avogadro's number, which gives me an answer of about 2.5-ish, okay, times 10 to the 24. So if I multiply that by this, which is about 4, times 10 to the minus 11, I get about 1 times 10 to the 14 joules. Do the same thing for so that was uranium. Do the same thing for the hydrogen, 2,1. So 1 fusion of that is going to be, 1 fusion event is going to be, where did we write it down? Oh, it's here. 3.6 times 10 to the minus 12 joules. Now, the number of moles you have in 1,000 is that divided by 2, which is 500. So the number of molecules you've got to have is 500 Na. Which is about 3 times 10 to the 26. But you'll actually only have half of that because you need 2 of them to react. So the number you're going to have is about 1.5 times 10 to the 26. And that will give you how much energy? 1.5 times 10 to the 26 times this, 3.6 times 10 to the minus 12. Gives me an answer of about 5.5 times 10 to the 14. So if we're going to do the energy that the hydrogen gives you compared to the energy uranium gives you, you're going to have 5 times 10 to the 14 divided by 1 times 10 to the 14, which gives you 5 over 1, which is 5. So you get about 5 times more energy from the hydrogen fusion than you do the uranium fission, although they're very similar. So fission and fusion reactions release different amounts of energy. Discuss why it'd be preferable to use fusion rather than fission. Well, hydrogen is much easier to get hold of, and also the products of fission are radioactive, and so they're expensive and difficult to deal with and could become an environmental problem. Okay, hope that helps.